So now that we've gotten the nuances of temperature out of the way, let's talk about this quantity of heat. I've alluded to it several times in this chapter as well as in this class. This thing called heat is a form of energy. I've talked about thermal energy before. We know that if there's friction in a system, it's going to take away from, say, some of the kinetic energy an object has, and that energy went into the form of thermal energy. Kind of a classic experiment right over here. If we have a mass on a weight on a frictionless pulley turning some paddles in a glass of water, then the amount of work that this mass does on the water is going to be proportional to how much the temperature is going to rise in that in the water system. So we can write this heat energy, that's going to be that symbol Q, as being related to the mass of the object that you're changing the temperature of. It's going to be related to the change in temperature. It's also going to be related to the specific heat, which is also going to be known as the heat capacity of an object. And I'll talk about this a little bit more on the next slide. It's really material dependent. So very important equation to know. Now this Q, it is a form of energy. So suppose you go to the very top of this building here and you throw off, say, a frozen chicken. Initially, this frozen chicken has some potential energy. It's mass times gravity times the height. Now at the very bottom, now the all of the energy, if it doesn't bounce, is eventually going to go into thermal energy. So mass times the specific heat capacity of the frozen chicken, and a change in temperature. So theoretically, we could calculate the change in temperature knowing how high of the building we dropped it off of. So this creature called heat capacity, or specific heat, as I had on the last slide, is going to be this C constant here. It's going to be material dependent or substance dependence, and table 17.3 is going to show what the specific heat is for various substances. One that we'll use a lot is going to be water, which is going to be 4190. The units are going to be joules per kilogram degree Kelvin. Essentially, it gets the joules from here, the kilograms and Kelvin from this side of the house. So, very important equation right here. Suppose I said, you know what, I've got myself 1 kilogram of water, and if I increase the temperature, so a change in temperature of 20 degrees Celsius, this is also going to be 20 degrees Kelvin. How much heat did I need to add to this? Well, my heat is going to be equal to my mass times my specific heat times my change in temperature. So my 1 kilogram multiplied by 4190, then that's joules per kilogram degree Kelvin. Because this is a change in temperature, I can get away with using Celsius because 20 degrees Celsius is also 20 degrees Kelvin. So I can put in a 20 right there, and I can calculate this out. And I get 83,800 joules. That's a pretty big number. It takes quite a bit of energy to heat water up. Let's look at something like lead, which has a specific heat capacity of 130. Largely because of the specific heat capacity of water, it takes a lot of energy. Something like lead, with a very low specific heat capacity, it's going to take a lot less energy to raise the temperature of 1 kilogram of this substance by 20 degrees. Metals generally have lower specific heats than, say, water. So what I said on the last slide, where I had the amount of heat you add to a system is going to be equal to its mass times its specific heat times the change in temperature, that is only going to hold true if all of my material stays within the same phase, where the phases are going to be solid, liquid, or gas. When we have a phase change, we're going to have another type of energy to worry about, phase change being a transition from one to the other. If we take a look at the plot of temperature versus, it's got it in terms of time, I'm going to say temperature as terms of heat input, then suppose I have some ice and it's at negative 25 degrees Celsius, and I add some heat, then the temperature is going to change, and you'd expect it to be linear from what we know on the last slide. At 0 degrees Celsius, the ice is going to start to melt, but the temperature is not going to go up. We're going to have both ice and liquid water in the same phase right here. You have to continue to add heat until all of the ice has essentially changed into the liquid phase. Then we have liquid phase. We're adding more and more and more heat. The temperature is going to go up. We hit the boiling point, and we're going to have some water in the liquid phase and some water in the steam phase. We need to keep on adding and adding and adding and adding heat until finally all of the water is now in the gaseous phase, and we're going to have our gas right here. This amount of heat we have to add during this phase and that phase right there is characterized by this very important equation right here that says the heat is going to be equal to the mass of the substance you're adding the heat to, multiplied by this L right here, which is going to be called the latent heat. This latent heat will be called the latent heat of fusion when we're doing a solid to liquid phase change, or the latent heat of vaporization for the liquid to gas phase change. So this table right here, table 17.4, shows you some of these latent heats of vaporization and fusion. I'll talk about water because that's kind of one we're mostly familiar with. So here we have the latent heat of fusion, that's the solid to liquid, and here we have the latent heat of vaporization, the liquid to gas. And you can kind of see that it takes 10 times the amount of energy to go from the liquid phase to the gaseous phase compared to the solid to liquid. What this also kind of means is if you have water that is 100 degrees Celsius and you have steam, gaseous water vapor, that is 100 degrees Celsius, and suppose you just have 1 kilogram of that, then the steam, while it's the same temperature as the water, it's going to have a heck of a lot more energy than the water. It's going to have 2256 times 10 to the third joules more energy, because we're talking about 1 kilogram of water. So if you had to choose between getting 100 degrees Celsius water on your hand and steam, go for the water. So let's take a look at setting up a few problems, and I'll leave it up to you to complete the problem. Here we have a tea kettle that has some mass associated with it, and it has some water, and we know the mass of the water. And we're asked how much energy does it take to raise the temperature from 20 degrees Celsius to 85 degrees Celsius. And you say, okay, well, I know that the water is not going to undergo a phase change, and the aluminum tea kettle is not going to undergo a phase change. It's not going to melt on me. So the amount of heat that it takes is going to be how much heat it takes to change the temperature of the aluminum, plus how much heat energy it takes to raise the water to that temperature. And we know the relationship. It's going to be the mass of the aluminum multiplied by the specific heat of the aluminum multiplied by the change in temperature of the kettle. Make sure that says aluminum. Plus the mass of the water, specific heat of the water, and the change in temperature of the water. And the change in temperature is simply going to be 20 and 85. It's going to raise it by 65 degrees Celsius, which is also 65 degrees Kelvin. And I've given you the specific heats up here. So we can then just go ahead and use this equation to calculate the amount of energy it takes to raise the temperature. Let's take a look at solving this problem. It's actually a calorimeter problem. We have some copper with some mass, it's got some water in there, it's got a piece of ice, that's new, and we're going to drop in a piece of lead that's at a high temperature, and we're asked what is the final temperature of the system. The key to solving this is actually going to be an isolated system, so there's going to be no heat flow into or out of the system. So all of the energy in the system must add up to be equal to 0. So the energy of the copper kettle plus the energy of the water plus the energy of the ice plus the energy of the lead, PB is going to be a symbol, must add up to be 0. We know that the lead is at a higher temperature. Temperature is going to drop, so when we go ahead and calculate this guy out, it's going to be negative, and these guys right here are going to increase their temperature, so they're going to gain energy. So we know that we can write the copper kettle, the copper container is going to be the mass times the specific heat of copper times the change in temperature of the copper kettle. We're going to have some water. That water is going to have some mass associated with it. It's got the specific heat of water, change in temperature. Now we're going to have the ice. The ice is a little bit more complicated because first we're going to have to melt all of that ice. So we're going to have the mass of the ice multiplied by the latent heat of fusion for ice. So now the ice has been melted. Now we need to say all that ice is going to be water. It still has the mass of the ice, but now I need to raise that up to the final temperature. So now it's melted, so I'm using the specific heat of water, and now we're going to have the change in temperature. And lastly, we're going to have the lead. So we're going to say that that's going to be equal to the mass of lead multiplied by the mass of the PB, specific heat of lead, PB, and now the change in temperature of the lead. So taking a look at this, the change in temperature of the lead is going to be T final minus the initial temperature of the lead, 255 degrees Celsius. The change in temperature for the water, well, and the copper kettle and the ice, we know that all three of those are in thermal equilibrium, and we're not told that the ice is lower than 0 degrees Celsius, so we're going to assume that the ice is at 0 degrees Celsius, so also must be the water, and so also must be the copper container. So the change in temperature of the copper is going to be equal to the change in temperature of the water, and that's going to be equal to the change in temperature of the ice, and that's going to be the final temperature minus 0. And I've listed the specific heats right here, so I've set everything up you need to solve this guy. You're going to kind of see that the change in temperature of the lead is going to lead to a negative a negative energy value for the lead, and all three of these guys are going to have a positive guy, and we can then solve for the final temperature. So now let's talk about how heat can actually flow from one body to another body. Heat is always going to flow from the hotter body to the colder body. The first way that heat can flow is through conduction, which is essentially there's going to be contact. I mean, if you want to heat up some water on the stove, you put the water in the pot and you put it onto the stove, so there's some contact there. Everything that we're going to do in this class is going to be steady state flow. We're not going to have any weird funky flows. So here we have a body that's at a hotter temperature. It's got some heat energy associated with it, and we can pretty much think about taking a hose and connecting it between these two bodies and say how much heat is going to flow per unit time. so a change in heat per unit time, how much is flowing through my hose. Well, if I consider just having a single hose, I can figure out how much heat is flowing through that hose. If I essentially take my single hose and I add a second hose, I've essentially doubled the area that the heat can flow through, so I can get more heat flow if I increase the area. Similarly, if I take the hose and I make it a longer hose, I'm going to decrease how fast the heat flows from one side to the other because it has to travel a longer distance. In general, we can say that this heat flow right here is going to be equal to a thermal conductivity, which is essentially how well does the heat flow through material. Each material is going to behave differently. You know that metals are going to conduct heat a lot better than, say, wood. So this thermal conductivity is going to be a property of the material. You can kind of see the thermal conductivities over here. The units are watts per meter per Kelvin. The surface area, so how large is the tube that my heat is flowing through. The temperature difference, if you have a huge temperature difference, the heat's going to flow a lot faster. If you have a very small temperature difference, the heat's not going to flow very fast. Or if these are the same temperature, then you can see that heat is not going to flow at all because temperature hot would be equal to temperature cold. And all of these guys are going to be divided by the length. So now we have an expression that describes the heat flow, dq dt, also given the symbol H, the heat current. We can also talk about, this rod here is going to have a temperature gradient associated with it. Obviously the rod right at this point right here is going to be at the temperature hot. Right over here, the rod's going to be at the temperature cold. So this little piece of the heat current expression right here is actually also known as the temperature gradient along the rod. We can consider temperature gradients that are not linear, but we'll save that for future classes. So we can take a quick look at a cooler on the beach. It's got the sun beating down on it. We can look at how much heat flow is going to flow through the styrofoam cooler. If we choose to use styrofoam because it has a great or a fairly decent thermal conductivity, it's going to be fairly low compared to, say, metal. It's going to have a very high thermal conductivity. So I've written the heat flow as equation from the last slide simply to save me a little bit of time. We can look up that the thermal conductivity of styrofoam is going to be 0.027 watts per meter squared, or watts per meter Kelvin. I know that the surface area is going to be 0.8 square meters. The temperature difference is going to be 30 minus 0. So temperature difference is going to be 30 degrees Celsius, also 30 degrees Kelvin. And then the thickness is going to be 0.02 meters. And I can calculate my heat flow to be 32.4. It's going to be a joule per second, so it's going to be a watt or a joule per second. Now the interesting thing is suppose you know that the cooler sits out for 3 hours. You could then figure out, essentially you take this heat flow, you multiply it by the time, convert that into seconds, and you can figure out how much energy has flown through the cooler. And if you were interested in figuring out how much ice was lost, it would be the mass of the ice multiplied by the latent heat of fusion of the ice. And the book continues to work that problem, so I highly suggest you take a look at that. We can take a look at two bars that are end by end. There's going to be a hot side and a cold side. Something that these two objects are going to share is they're going to essentially share how much energy is flowing through them. So their energy per unit time must also be the same. So the energy that flows into the steel must flow into the copper, and the energy is again going to be flowing in that direction from hot to cold. So we can say that the heat flowing through the steel must be equal to the heat flow of the copper. We can use that to figure out what the temperature is at the junction, and then we can solve for the heat flows as shown in example 1712. If we arrange our bars just a little bit differently and we have the same hot reservoir and cold reservoir over here, in this case it becomes quite a bit simpler. We're going to have heat flowing through the copper, we're going to have heat flowing through the steel, and we can say that the heat flow for the entire system must be equal to the heat flow of the copper plus the heat flowing through the steel, and then simply use the expression Ka delta T divided by length for each one of these guys, and we can solve for the total heat flowing through the system.